Hi, this is Mrs. Wiederholt, and welcome to my lesson video on graphs of polynomial functions. Now let's get started. First, let's look at a few of the graphs of polynomial functions that we do know. The graph of a constant is just a single point on your graph, and the degree would be 0. The graph of a linear function is a straight line, and its degree is 1. The graph of a quadratic function is a parabola, and its degree is 2. Now let's look at a graph that might be less familiar, and that's of the cubic function. And its graph would look something like this. And its degree is 3. Next, the quartic function can look similar to a W when graphed, and its degree is 4. The final graph we're going to look at is of the quintic function. Its graph can look something like this, and its degree is 5. Now, what about a graph that looks like this one? Does it look similar to one of the graphs on the previous page? If you guessed quartic, you're correct. Now, I want us to look at several characteristics of this graph. First, let's look at the x-intercepts. Okay, note that the x-intercepts of this polynomial function are at -4, 0, -1, 0, and 3, 0. Remember that the x-intercepts are when y equals 0. So these make sense when you look at the factored form of the polynomial. So here it is right here in factored form. And you can see if you set x plus 4 equal to 0, x would equal -4, which is right here. If you set this one equal to 0, you get x equals 3, which is right here. And then we have x plus 1 squared. And if we set that equal to 0, we have x equals -1. Also notice that each factor has an odd exponent when the graph passes through the x-axis, and it has an even exponent when the function bounces off the x-axis. So let's look at this on the graph. Right here where x equals -4, that represents the factor x plus 4. And as you notice, the graph is crossing through the x-axis. Over here, where x equals +3, that represents the factor of x minus 3. And again, we see our line crossing through the x-axis. Now, each of these factors has that invisible odd exponent of 1. And right here, where the graph bounces off of the x-axis, that represents a factor having an even exponent, and in this case, 2. Now let's look at the y-intercept. Now note that the y-intercept is 0, -12, and the y-intercept is where your graph or your curve crosses your y-axis. Now remember, there can be only one y-intercept. If there's more than one, then you don't have a function, and we know this because of the vertical line test. Now let's discuss the end behavior. Basically, all end behavior is it's stating that when x is going towards -infinity, what is y going towards? When x is going towards +infinity, what is y going towards? So that's what our end behavior is. In this example, when x is going towards towards -infinity, what is our y value going towards? It's going towards +infinity. So that's our end behavior for this one right here. Now, what if x is going in towards +infinity? What is our y doing? It's also going towards +infinity. Now let's look at some more characteristics. We are going to look at several types of polynomial graphs. The first one is the even degree polynomial with a positive leading coefficient. First, let's talk about the ends. Now on this one, we have an end right there, and we have an end right there. The ends of this graph will help us know the end behavior. Now let's talk about the bumps or turns. In this case, we have a bump or a turn right here. Now, the degree of your function will always be 1 greater than how many bumps you have in your graph. Now let's see if we can fill in some of these blanks. If we look at our end behavior, as x approaches negative infinity, f of x or y is approaching what? Okay, so here's our x approaching negative infinity. It's going leftward and upward. So that means our f of x is approaching positive infinity. Now for this one, as x approaches positive infinity, f of x approaches what? Well, if I go back to this side of my curve, this is the curve that is approaching, or the x value is approaching positive infinity. What is my y value doing? It is also approaching positive infinity. Now, let's look at the degree. Now remember, just a few minutes ago, I said that the degree is determined by how many bumps you have in your curve, and that your degree will always be 1 greater than the number of bumps. Well, in this curve, we have 1 bump, so our degree is 2. This graph represents a function to the second degree. Now for the leading coefficient, I want you to be able to determine if the leading coefficient is going to be positive or negative. Now in this example, we know in this even degree polynomial, our curve starts up here and it heads downward and then goes back up. Now in this case, if you start up high and go down and back up, that means your leading coefficient is positive. Now if we were to have started down here and our curve went up and back down, that would mean our leading coefficient is negative. Now our domain and range should be pretty easy for us because this is actually a parabola representing a quadratic function, and we've done this many times. So our domain is from negative infinity to positive infinity. And our range is going to be from the k value, or the vertex, the y-coordinate of the vertex, which looks like it's at -2. So in this case, our range will be from -2 up to positive infinity. Now let's look at our next example. In this graph, we have an end right here, and we have another end right here. And this graph actually has 2 bumps. And so that's going to help determine the degree of our polynomial. So for our end behavior, we need to look at what x is doing. So as x approaches negative infinity, what is y doing? It's also approaching negative infinity. And as x approaches positive infinity, which is this right here, if you see, it is going downward, but it's also going to the right towards positive infinity. What is our f of x or our y value doing? It's also approaching negative infinity. Now for the degree. Now remember, we use our bumps, and in this case we have 2 bumps, which means our degree is 1 greater. So this is a polynomial to the 3rd degree. In our last example, our graph started up high and ended up high, and so the leading coefficient was positive. In this example, our graph starts low, and what does it do? It ends up low. Yes, we've had our ups and downs, but it started out low and it's going to end low. And that means that this polynomial has a leading coefficient that is negative. Now before we move on, I just want to point out one more time that both of these examples are even degree polynomials. And so basically with even degrees, if you start high you'll end high. If you start low, you'll end low. Now for the domain. On this one, our domain goes from negative infinity to positive infinity. And our range starts at negative infinity. It goes up to what looks like about 13, and then it comes back down. So 13 is our high point, or it's our maximum point. Okay, now let's go on and look at some more examples. These two examples are going to be examples of odd degree polynomials. So first we're going to start here where we have an odd degree polynomial with a positive leading coefficient. Now with odd degree polynomials, how we determine the leading coefficient, which we're going to do that first this time for both of these, is it's a little different. This time with odd degree polynomials, if we start out low and end high, we have a positive leading coefficient. If we start out high and end low, we have a negative leading coefficient. I kind of think of this like climbing a mountain or climbing a hill. You start out at the base, and yes, you might have some ups and downs, but ultimately you get to the top. So you're going upward, you're going in a positive direction. With negative leading coefficients, it's like you're at the top of the mountain and you're working your way down to the base. So that helps me a little bit, and I hope that helps you. Now for the end behavior. Now in this one, as x approaches negative infinity, which remember, I know it looks like I'm going almost directly down, but I'm not. I'm also heading towards the left. So that means as x approaches negative infinity, my y value, or f of x, is also approaching negative infinity. And as x approaches positive infinity, which yes, this is slightly going towards the right, as x approaches positive infinity, f of x also approaches positive infinity. Now for the degree. So let's look at the bumps. I have two bumps, one here and one here. So that means my degree is 1 greater than that. So that means I have a polynomial to the third degree. Now polynomials to the third degree are called cubic functions. And cubic functions always have a domain of negative infinity to positive infinity and a range of negative infinity to positive infinity. And if you look at the graph, you can see that. Now, what do you think the end behavior is for this graph? So think about it. We're going, as x approaches negative infinity, what is f of x approaching? It's approaching infinity. And as f of x approaches infinity, positive infinity, what's happening to our f of x? It's actually approaching negative infinity. In this graph, we actually have, it's a little hard to tell, but we have 4 bumps. And so those 4 bumps means that we have a 5th degree polynomial. And our domain and range for each will be negative infinity to positive infinity. Now, maybe you're starting to notice, but if you have odd degree polynomials, your domain and range will always be negative infinity to positive infinity. Now, what we've learned today are just some basic characteristics of polynomial graphs or polynomial functions. I hope this video has helped you, and I look forward to working with you again. Bye-bye.